So, good afternoon, everybody. Thank you all for joining the webinar on digital twins today. First of all, I would like to ask all the participants to keep your microphone off during the presentations. The same for the camera. If you have any questions, at the end of each presentation, we will have some time to answer those questions. Please put your questions in the chat, or you can raise your hand and I will give you the possibility to talk and ask the question yourself. Today we have 3 presentations. The first is Klaas Gadeyne. He's a fellow researcher at Flanders Make, and he will help you to understand the meaning and the concepts behind the digital twins. After that, Agusmian Ompusunggu, a senior researcher of Flanders Make, will show you a successful story of an application of digital twins. And finally, Francois Strykers, the CEO of Global Skills, and Paul Balkenars, that is a research fellow at the UCLL, will explain you how Interreg can help you to integrate digital twins in your companies. Let's start with our first presentation. Enjoy it.
Good afternoon, everybody. My name is Klaas Gadeyne. As Gabriel introduced, I'm a research fellow at Flanders Make, and I also lead the Smart Factories team at Flanders Make. And today I'm going to give you some background on the new hype, digital twins. And why do I say hype? Because indeed, digital twin, most of you will know that this clearly is a buzzword. To illustrate this, you can see on this slide the Google Trends for the term digital twins, which has been very steadily rising since the year 2015, 2016, and has become one of the more popular search terms in Google over the last years. Next to this, another good source of information for detecting trends and hypes is typically the Gartner Top 10 Strategic Technology Trends every year. Well, if we look at the technology trends for last year, hyper automation was on number 1, and hyper automation means, of course, automating your organization, and Gartner explicitly mentions, you can see it here, hyper automation often results in the creation of a digital twin of the organization. Now, what is the consequence of being a buzzword? The consequence of that is, of course, that everybody is trying to use the term digital twin in a way that suits him or her. And to give you some examples, how diverse these terms can, or how diverse the usage of these terms can be, I give you a couple of examples. This is a first example. It's coming from Siemens, where the term digital twin is used in the context of virtual commissioning. So virtual commissioning, which means testing the design of a particular product, in this case an engine, in order to make sure that it will meet all of its specifications once it is actually produced. A second usage of the term is coming from a different usage where we have a physical system and people want to be able to answer questions about this physical system to perform what-if analysis or trade-off analysis. In order to do that and not to have to experiment with the physical system itself, they are building a model of that system using physical principles. Of course, in order to make sure that this model accurately represents the real physical system, the model, which has some parameters, is tuned by capturing sensor information and by using that sensor information to update the parameters of this physical model. So this is a second example.
I would like to give you some highlights of the discussion, and then my plan was that we could deep dive a little bit into.
Okay. Sorry about that. A third example of digital twin usage is a software product. It's coming from a company we all know, Microsoft. And this is a screenshot from a software product which is called Microsoft Azure Digital Twins. Basically, this is a software product whose main purpose is to organize different and hierarchical complex data sources. And a fourth example of digital twins are digital twins of an instance of a fleet of systems where you build a digital twin of each of the set of cars here in order, for instance, to estimate all of their positions. Now, as you can see, there are many definitions of digital twins, and there's still some noise. And there are many definitions of digital twins, and many of them are not complementary. So what I'm not going to try to do today is to give you a definition of digital twin, because it's quasi impossible to give you a definition that suits all of these uses. However, in order to increase the understanding of people that are using the term digital twin, my goal today is to equip you with some knowledge and some tricks that can help you to understand what other people mean when they are using the term digital twin by asking the right questions, or when you yourself want to use the term digital twin in a particular context, to make other people aware of what you mean exactly. And how can we do that? My goal is to do that via a unified description mechanism for digital twins, where there are, in my opinion, three aspects to consider. What's the purpose of your digital twin? What's inside of your digital twin? And how do you deploy that digital twin on an IT architecture? All these three aspects, they can be visualized in an architectural description. And I'm going to show you some examples of such an architectural description. After explaining how to do this, I will summarize it, and I will not give you any homework. Okay, what are the three things to keep in mind when you're discussing about a digital twin? One, and maybe the most important one, is what is the purpose of, or what are the purposes of your digital twin? That means, who are you making this digital twin for? And what does that person or system wants to achieve with the digital twin? Once you know what the purpose is, and you can do that considering even the digital twin as a black box. A second thing that you can explain is what's inside your digital twin. Typically, in your digital twin, there will be a combination of data and models. And finally, of course, those data and those models, they need to be deployed on IT or IoT hardware, and explaining how you deploy your digital twin can also tremendously help in explaining people what you actually try to achieve with your digital twin. Now, coming back a little bit in more detail on each of those aspects, to give you some examples and things to think about on these aspects, is starting with the purpose. You have digital twins on the product, as we have seen, but there are also digital twins of the production system. So make clear for which asset you are building the digital twin. And maybe you're even building a combined digital twin of both the product and the production system. A second thing which is often forgotten when working around digital twins is to mention explicitly for which life cycle phase of your product that you are building a digital twin. And there are two important distinctions to make. On the one hand, you have digital twins which are mainly used in the design phase. So the example I gave earlier on virtual commissioning is one of them, where you are building a digital twin, often when there is not a physical prototype available, or when there's only one physical prototype to do some testing available. On the other hand, you can also build a digital twin for the production life cycle of a product, for the operation of the use phase of that product, or even for the recycling phase. In that case, often you will not have to build a single instance of a digital twin, but you will have to build an instance for every car in your fleet. So there's a lot of digital twins, and of course this comes typically with its own phases. Going to the second point, what's inside of your digital twin? As I mentioned, both models can be inside and data. Looking first at models, then there's often, we can make a distinction between digital twins, which are based on physical models. And with physical models, I mean analysis models which are built on the principles, the laws of physics. Some of you might know, for instance, the Modelica or Simulink or Simscape or other tools to explicitly model the behavior of such a system. On the other hand, what we also often see are digital twins which are based on black box models. Those are analysis models which are created purely by analyzing the data and without any physical principles behind. And here also, very often in reality, a combination is made, and those are called so-called gray models, which are a combination of the physical white box models and the black box models. As I mentioned, there's not always a model inside, and I'm going to give you a concrete example here of one particular twin that, as Flanders Make, we are doing research on. So imagine the production of a particular part of a system. And one of the production steps is performed by a CNC machine. So the CNC machine takes a casted part, and casted iron part, performs some manipulations such as drilling holes, milling surfaces, and ends up with a finished part of that system. For many parts, geometric quality is very important. And as such, we see that companies, production companies, typically have a lot of steps in place that are related to quality control. In this case, in that company, in the CNC machine, there is an internal probe that is used for every product to make a first assessment if the geometric tolerances are met or not. Secondly, when the operation is finished, an operator is verifying the critical dimensions of this part using an e-caliper, and also collects data on the quality of the part as such. And finally, for let's say 1 out of 10 parts, the part is sent to a coordinate measuring machine that can offer very detailed information on the geometry of the part. Now, this is all very nice, but of course, all of the quality measurements, the result of the quality measurements is that the lead time and the throughput of our production system is decreasing. So now what if we are trying to build a digital twin in order to ensure that we can keep the same quality, yet reduce the number of quality control? And how can we do that? Of course, using some data and using an artificial intelligence algorithm. So where the goal would be to come up with a virtual assistant. You could realize it, for instance, via some dashboard, and that dashboard can indicate to an operator whether you are in a green zone and you don't have to carry out too many measurements, an orange zone or a red zone, where one of your indicators is probably indicating that you have a problem, and where there is a need for carrying out more measurements. Now, Okay, I was kicked out. Can anyone confirm that you can still hear me?
Yeah, I can hear you.
Yes, now we can.
Okay, I was kicked out for a second or so.
Yeah.
I will continue. What I was saying is that when you want to realize such a system, you will need to build an architecture. And in our online digital twin, of course, we will have a model that can predict to the operator whether he's in the green, red, or orange zone. On the other hand, before that can actually be realized, what we will need to do is we will need to capture data from the CNC machine, from the measurement devices, and for instance, also other things such as the ambient temperature, and capture and store that information in a set of databases. Why? In order, of course, to make that data available to a data scientist that can carry out analysis on that data, for instance, finding correlations between quality and certain settings of the machine, and as such use that data in order to build a predictive model that then can be used in the online digital twin. Now, this in turn, this part is also a digital twin and is also called a digital twin because it offers also a digital view on our physical system. This is the operational things zone, by the way. So it offers a view on our physical system via a digital way, namely the digitalization of the captured data. Now, the third part is how do we deploy those models and data? And there again, it can be very diverse. On the one hand, deployment can be locally on an edge device and only on an edge device. We have here an example of an adaptive cruise control system where a digital twin is built that is used to estimate the behavior of the car which is driving before you, and as such can be used to control your own speed. Well, such a digital twin can typically be deployed on an embedded device only, and it's a very local way of deploying a digital twin. Next, what we can imagine, for instance, the production case already gave you a flavor on that. If we have a full production site with operators, with control systems such as the PLCs, with a set of other measurement devices, all that data needs to be processed, either wireless, either wired. Some of it can happen on the edge. Some of it can be transferred to the cloud. From the cloud, we can go to the data scientist or to a local storage on a PC of a data analyst, or the dashboarding can, for instance, be shown on an iPad to an operator. So this is a very complex Internet of Things architecture, which is also realized to, which is also used to realize one or more multiple twins. So I discussed now purpose, what's inside, and technological implementation. What I'm advocating is when you're discussing digital twins, it can help to clarify what you mean if you illustrate these three things on an architectural diagram. How can you do this? On the one hand, by illustrating what is your asset, what info are you sharing with your twin, what data are you sharing with your twin. Is there a feedback loop from your twin to your device? For instance, is it a device that can be configured or controlled, and can you use a digital twin to control a setting of that device? And to illustrate clearly the purpose of your digital twin, namely, who am I building this? Who am I building this twin for? And potentially, it doesn't necessarily have a single purpose, but it can also have multiple purposes. And let's not forget that you can also build digital twins of a fleet of devices, so there is not necessarily a single asset. A second part, which is the implementation view. can be used to show how this is actually realized by showing, for instance, how your models or your data are deployed in the edge or in the cloud, and who are then the physical persons that are going to interact with your digital twin. To make this a little bit more concrete, I will show you one example. This is an example not coming from the production, but from an actual product. And it's on digital twins of transmissions. Namely, a transmission, everybody, I guess, knows a transmission, which is in most vehicles. And a transmission constitutes of more than two parts, but two parts are often very critical because they can break down. On the one hand, these are bearings. On the other hand, these are typically gears or gear sets. Now, when people want to avoid that there is a downtime or an unforeseen breakage of such a transmission, it is useful to think about predictive maintenance. And as such, one thing you need for that predictive maintenance is to be able to estimate when a particular part is going to break down. Often this is called remaining useful life estimation. Now, if we're going to build a digital twin, or if we do want to build digital twins for this system, analyzing this, we can say that basically there are two types of digital twins for this remaining useful life estimation. One is the data digital twin, as I would call it, where actually you are going to collect all of the data from for instance, various acceleration sensors which are mounted on your systems, and collect that data, offer it to the data scientist. And one way of deploying it could be that you use some low-cost monitoring software in order to capture that data, and you use a cloud service with a time series database in order to store all of these time series. As such, you can make it available to the data scientist. The second type of digital twin is the online digital twin. This digital twin is actually serving the operator. And how it works by collecting streaming data from one of the devices, possibly pre-processing it, for instance, removing some noise, and then putting it inside a model. In this case, the model is a neural network. And using that neural network to produce an outcome on the remaining useful life, which can then be shown to the operator on a dashboard. For instance, realizing this by using Grafana, which is a software for making easy dashboards, and showing that to the operator on an iPad. And as such, this is the example of how an architecture of an online digital twin for remaining useful life estimation can look like. Okay, now I've shown already how you can illustrate your digital twin. Another important thing is typically, whether you're a researcher or a company, you want to show what challenges or what things you are inventive in, what you are doing new. So that's also something that you need to stress, in my opinion. Stress what challenges that you are dealing, and those challenges, they can be related to the purpose of the digital twin. So learning can be difficult. There can be a large challenge in formalization of knowledge. Think about operator knowledge, for instance, in a production system. Or the challenges can be rather from a technological nature, where as a company you need to get acquainted with new technology on the one hand, or when you are building, for instance, a digital twin of a complete fleet of systems, where there are large challenges in getting this computationally okay in terms of the necessary storage and computing power. And of course, sometimes the challenge can also be on both levels. One example is a lot of companies don't only have a single asset, but they have a complete product family of assets. And then it is important to be able to realize those digital twins of your product family in an efficient way. So make your challenges explicit. Okay, and now I'm at my last slide for today. So my goal today was to give you one important message. Instead of debating what's the most appropriate definition of the term digital twin and not understanding each other, try to enhance communication between people that are using the term by clearly showing what you mean via an architectural overview. On that architectural overview, you indicate what's the purpose of your digital twin, what's inside, what models, what data are inside, and how do you realize it from an IT point of view. And also illustrate what challenges that you want to tackle using your digital twin or for realizing your digital twin. Thank you. Are there any questions? I think I can spend 1 minute for taking questions.
You can take more than 2-3 minutes, Klaas, don't worry. So there are questions. I don't see questions in the chat. Okay.
No questions?
If we don't have questions, I propose that we move to the next presentation. So Agusmian, the floor is on you.
Okay, thank you, Gabriel. Thank you, Klaas, for giving the introduction of digital twin. Let me share my screen. Okay, so as Klaas as explained, so there is no single definition of digital twin that can accommodate all possible applications. So, and one of the applications that he already mentioned in his presentation is predictive maintenance. And today I would like to present one of our success stories related to this field, vibration-based condition monitoring of an expander machine. Yeah, so one of, let's say, challenges to start building reliable and effective predictive maintenance strategy in your company or in your organization is that to find critical assets, as Klaas explained earlier. So what are the critical assets in our companies, organizations that can give a big impact to our business? This is the first step that we need to clarify. So once we have identified critical assets, and then we can talk about how to build digital twin that can serve for predictive maintenance. And this success story came from one project where in the beginning we were struggling with the company to identify the critical assets, and then based on their business data, finally we could identify the critical asset. In this case is expander machine. So they only have one expander machine in their production lines, and you can imagine that if this machine breaks down unexpectedly, this will lead to quite long downtimes, a few days downtimes. And for this machine, the production rate is about a few tons per hour. So if this machine breaks down, and so you can imagine that how many tons you lost. So what they typically do, so they perform time-based maintenance or preventive maintenance. So every week they send technicians. And then this technician spends about 4 hours a week. So you can imagine that every year, so they spend 208 hours, which are possibly not necessary. And what we offer actually in that project is a condition monitoring system using low-cost sensors, because again, sensor or investment is one of the bottlenecks to implement this maintenance strategy. It's not free investment. We need to invest technologies and also human resources. And another thing that we propose is a software toolbox that can transform what we measure into actionable information, because we collected a lot of data, but for for the end user or operator or for the maintenance manager, they need concise information that they can use to make decisions. And as you can see on the left figure, so the machine that we equipped with a number of sensors, as you can see that this machine also consists of different critical elements like electric motor, a gearbox, and the expander itself. So we equipped them with some sensors. And now the goal is to establish a digital twin that can serve for scheduling your maintenance. And here, this is a specific architecture for this application. So again, there is no generic architecture that can be applied to all applications. So again, this is very specific to this company. And so from this data that we collected, and then as you can see that we transform this huge amount of data into a very informative indicator. So we call it health indicator. And as you can see that before the failure happens, so the health indicator gave very low value, and then the failure took place, and then they replaced the broken parts, and then as you can see that the health indicator goes to high value. Just for your information, this is what happened actually when the failure took place. So one of, I think, some blades came off from the expander machine. And what we have created through this company, so basically if we use this health indicator as a digital twin, so they don't have to send their technicians every week. So basically we can reduce the effort. So basically they only need to send their technicians when there is an alarm, when the health indicator drops to below to a certain threshold. And then because we continuously monitor the health conditions of these critical assets, so we can avoid unexpected downtime, and in this case we can minimize the production loss. And now they can migrate from traditional time-based maintenance into condition-based maintenance. Okay, what we can offer for companies with similar problems. So we can offer our expertise in defining sensors and hardware, because one of the challenges in this kind of problem, okay, we have an asset, but we need to also impose some domain knowledge in order to define and select relevant sensors and relevant data acquisitions, because if you don't have this knowledge, from our experience, potentially we don't collect the right data. So again, if you want to build robust and reliable system, so we need to also not only applying data-driven technique, but as Klaas mentioned earlier, gray box approach. When we combine physical insight or domain knowledge and data, this will typically, from our experience, provide reliable result. Okay, so besides sensor and hardware expertise, so we can also offer the software toolbox that we have developed since the past years that can help you to build a digital twin for maintaining your critical assets. and this software toolbox is customizable. We can easily integrate this with your existing data ecosystems, for instance. Yeah, that's all. So it's a short presentation about yeah, the result that we achieved with the company from a project. If you have questions, feel free to post in the chat.
Yeah. Please, if you have questions, you can raise your hand, and I will give you the. I will let you speak directly.
Yeah, or indeed, or you can raise your hands, and then yeah, we can give you floor to talk.
Yeah. Yeah, there's a question in the right in the chat.
Okay, thanks, Agusmian. Can you elaborate how is the presented condition-based maintenance digital twin different compared to traditional monitoring applications? Yeah, so for so the difference or the fundamental difference is that with the traditional monitoring application, so you always involve an expert. An expert has to interpret the data. So, for instance, with the vibration-based technique, so you collect the data, and then you perform some with your portable device. You perform, let's say, envelope analysis or spectrum analysis, and then the operator or the expert has to interpret this and then make conclusions. What we offer here is fully automated, because we combine this domain knowledge and machine learning or AI really to automate the process. The second question, can you confirm that an actual breakdown needs to happen to put limits? Yes, so this is a part of fine-tuning your model, because in order to be able to reliably predict when this failure would happen, so we should have at least a full data set. So what I meant by full data sets, real data sets from the healthy state until until failure happens. And then in the next round, when we want to deploy this, and then we have already, let's say, historical data that can be used to build an initial model. That's critical. From the third one, from a more pure viewpoints, the difference between the gray box model and pure data analytics is the actual digital twin. I'm not sure if I understood this. Maybe from Paul Falconer. So maybe we can have another chat. The fourth one, challenge for single asset is to obtain enough data to establish verifier models. How many failures? How much failure data does? Yeah. So yeah, as I said, this is one of the challenges in this kind of project, is to really have a complete data set. So if we don't have a complete data set, what we typically do, okay, at least we can, so from our physical insights, at least we can say good or bad. We cannot predict when this will happen, but at least we can say if something goes wrong, we can trigger this, but we cannot say when this will happen. That's the minimum, let's say, output that we can generate with our approach. And then from Daniel Bora, thanks for your case presentation. Did you have already a real-time condition-based maintenance? How many times you need to collect? Yes, how many? And yeah, how many times you need to collect the data and have a reliable model? This is case specific. And so, for instance, if you have assets which typically last for a few years, imagine like wind turbine, like the structure of the wind turbine. So the design lifetime is about 20 years, for instance, and it doesn't make sense to collect the data every second, right? So you should, because you will generate huge amount of data. This will impact to the investments, because you need to foresee investment for your infrastructure. So you need to find a trade-off between between the what you want to achieve and the investment that you need to to put. And then from Hans Weitjens, how often does such machine break down? Yeah, when we executed the project, so according to the company, this machine would break down every a few months. So that was one of the reasons why we chose this machine. Yeah, and if it breaks down rarely, how do you have enough data to train a predictive model? Yeah, so if we really rely on pure data-driven technique, indeed. So basically, we cannot proceed further. That's why our approach is always trying to combine, domain knowledge, because for instance, if you talk about gears or bearings, so the physics of gears and bearings, as long as we are on the Earth, and as long as we are, on the Newtonian condition, so we can always apply this to any kind of machines. So that's very important. And then by combining with the with the machine learning technique, and then we can improve the predictions. That's always what we practically applied. And then the last questions, Agusmian, thanks a lot for the presentation. I assume you are using analog sensors with a further. Yes, so indeed we use analog sensors, low-cost analog sensors, basically MEMS based sensors, and we have different. So FFT is one of the pre-processing techniques, but again, depending on the assets that you want to monitor, so you can have different more advanced signal pre-processing techniques. So FFT is one, but in order to really, because in this kind of problem, the signal that you are looking for sometimes is really buried by the other sources, like in this case, like gears are typically dominant in this kind of applications. So if you don't use the right processing technique, potentially you miss that that information.
Okay.
The second question: do you apply? Yes. So we use apply. So basically, what we do, and so we have our set of signal pre-processings inspired by the physics and by our domain knowledge, and then once we pre-process this with the physical inspired data pre-processing, and then we apply an AI algorithm really to identify a certain information from the pre-processed data that you generate.
Thanks, Agusmian. Paul will do a question directly. So Paul, I suggest that you can open your microphone.
Okay, can you hear me?
Yes, I can hear you.
Okay, so I've been doing research where basically interoperability was solved by money and my time, and I still had interoperability issues left. And so I discovered that if you build systems and you build them towards their purpose, like in this case, getting the analysis, then you start to introduce constraints that make interoperability with the rest of the system very tricky and hard and things like that. Whereas if you limit your digital twin to just reflecting relevant reality and consider the rest of the system to be separate user of the digital twin, you get digital twins that are much more easy to integrate, interoperate, and so on. So in your case there, what I would consider the digital twin is only part of what you have been presenting, in the sense that the part that collects data and mirrors the relevant reality. The relevant reality is the twin.
Yeah.
Anything else that's looking into the data, making decisions about maintenance and things like that is not the digital twin, is the user of the digital twin, which of course is absolutely necessary to have something functional and valuable. If you don't keep those things separate, you will be stuck forever with digital twins that have to be able to pay themselves on their own.
Yeah.
So as you said, you pick a target which is high value, high leverage economically. If you don't keep your twin pure and you build this kind of closed system which does the whole thing, and you don't make the pure twin accessible to other purposes, then you will never be able to use twins system-wide for a lot of low-value purposes, which together probably can make up much more than the high-value target which you have now.
Yeah, I completely agree. So as Klaas explained earlier, so I think the digital twin should be driven by the purpose. So it's not the goal to model everything, right? Because it doesn't make sense. I think you should only model things that are relevant to your business.
Yeah, so your purpose defines what's relevant,
Wow.
and what's relevant defines what's your twin.
Yeah.
Your purpose doesn't define your twin. Reality defines your twin, and what's in your twin is what's relevant for the purpose.
What is relevant for your business? Yes.
And the big difference between doing that and just going for the purpose immediately is that it's easy to expand the twin with other relevant aspects without breaking any of the existing users. That's the main difference. If you have a twin which is already, say, deformed towards the purpose, and you need to use it for some other purposes, then the deformation will kill you. And then if you start sharing a twin between two purposes, and one of those purposes starts changing the twin to its purposes, the other users will break. That's where why it's important to have a notion of how to make your twin pure, so that it's really reflecting reality. It's not deformed by the purpose, but the purpose decides that, say, if your twin would be a map, and you have a certain purpose, and there are, say, sewages under your streets, and that's not relevant for your purpose, then it's not in the twin. If it's relevant for your purpose, it's in the twin. But what's in the twin is determined by reality, not by the purpose.
Paul, Agusmian, sorry for interrupting you. Thank you for your comments and your clarification. It was very interesting. However, we are a little bit ahead of the schedule.
Yeah.
So
late
in the schedule. I would just like to send a message here to all the participants is that we are looking for use cases for the project that will be presented in the next presentation. So if you want to participate and you have some interesting cases that in which you want to apply your methods, you can just contact us. You can contact me to this mail. I propose that we move to the next presentation. So Francois, the floor is on you.
Yeah, hello everybody. Just share my screen so you see my LinkedIn if you want to connect. So we'll have a quick chat about the project that we are leading currently with Flanders Make and some other partners. And also I will at the end of presentation give the floor to Paul, who happened to be one of the work package leader of the project. So first I have the honor to be the CEO of Jobs at Scale, which is a little structure active in Wallonia, Liège and Luxembourg, but also now internationally and with our dear Flemish partners. So our main mission is to develop high-level training on innovative topics, and we do that also in an innovative way. So we focus on strategic and innovative topics such as Industry 4.0 and digital twins. By the way, and also we do that by producing spot, MOOC, webinars, gamification, virtual and augmented reality, all new ways of learning approach to develop this training. But I don't want to speak more about jobs at skills. If you're interested, we are on LinkedIn, on Facebook, on Twitter. So feel free to connect if you're interested in what we do. And as we were interested ourselves in developing new learning approach in Industry 4.0 and mainly in digital twin, we had the initiative to depose an Interact program which is called Digital Twin Academy, and the webinar of today was organized in this framework. And I want to tell you more a bit about the project, so maybe you will be more interested and to get on board with us and participate in the various actions. So the first thing important is to say and to remind that the Digital Twin Academy project is being carried out within the context of Interact Euregio Meuse-Rhin and with the European Regional Development Fund. This is the principal financial support. They finance 50% of all the action on all the project, and also we have 11 regions that participate from Flanders, Wallonia, the Netherlands, and Germany that supports us with the other part of the money for the project, and also all our partners that also support with our own money. So Euregio, if you don't know it, it's the region you see on the right of the screen. So I won't detail all the region, but it's an area that gather Flanders, Germany, Holland, the Netherlands, and a part of Wallonia, the province of Liège. And we have been gathered together with 11 partners and major industrialists involved in this academy. So these are the finance partners. You see that there are academic research, also training centers, university and 4 university college, that engineer school mainly, that participate in the project. And also what is very important to us, and new industrial are very welcome to get on board if they are interested in participating in the way they want in the various work package. But you see that we are also supported by major top-level industrial from our region. So you see there are industrials like Siemens, ENGIE, also Federation of Enterprise like Agoria in Belgium, or Essentia, the chemical industry, Orange. So all these industrial partners, they participate in actions, webinars, seminar, but also, as Paul will explain after, in test cases of digital twin in real industrial environment. So what was the project objectives? We want to develop areas of excellence in key topics here in Euregio. We want to make qualitative leaps in terms of skills, because without the people, without the knowledge, as it has already been said today, it's very difficult to be the leader in process like the digital twin. And we made a choice on the digital twin. Why? Because these technologies are still very innovative and complex, and we observe the knowledge gap in teaching, learning, and training, research and development, and also integration and consulting in industries. So what we wanted to do is assembling energy around the twin and have a multi-partner project-based logic. So you see there are academics, research, training centers, but also industrial, all working together on this subject of twins. So how will we do that? We want to build an ecosystem, one project around the twins. So you see there will be awareness and dissemination actions. We will quickly have a website. I think it's for the next week or so. We will already also have pages of obviously on social media where you can connect and see the various sections. We will organize all around the Euregio seminar and conference. So this seminar conference should be in presential, but now, as you may imagine, we only organize digital actions. But as soon as we can reorganize presential events, it will be in presential, and also webinars that will be digital, only digitally. such as a webinar should be all along the project. There will also be development of courses, training for high school, bachelor and master students, lifelong learning and education for all the public, with that from the unemployed people to the professionals and even the executives and the CEO, and also basic research and applied research by the academic partners, and testing in real condition by conducting business cases with interest industrial partners. And another part, but which is more a bit outside the project, will be the incubation of value creation projects, so investment, startup, scale up, and financing research. So we have 4 work package in this project. I will quickly have an insight on the WP1, which is called Building the EMR Digital Twin Community. So we are currently, as I have already said, developing a DT website. Another part where experts can exchange on a day-to-day basis is a web platform, but where only expert identified and recommended by our partners can attend, which is called the DT network, and also classical digital communication by social media and so on, where you can follow and participate and exchange expertise and also resource or documentation on the twin. We will organize 19 webinars during the project, 18 workshops all around the Euregio, and 18 seminars that are prevailed. So a few dates. So you see, today we are the 28th of May. It was a webinar for Industrial by Flanders Make. You have another one by the NMWP, which is the German partners, the 10th of June, and then we get back to September. There are already actions that are organized. We will quickly send the all planning for the next semester, because some actions are still have to be planned. So this is for the WP1. The WP 2 and 3, which is led by the Fachhochschule Aachen in Germany, will be the development of joint innovative digital twin training program with new learning approaches, such as MOOC, so massive open online courses, so a digital learning course that is open to everybody and which is free, and also SPOC, so small private online course, so it is a course for 15 or 20 people, all online, that you can attend wherever you are, but also webinars as today, live conferencings and virtual classrooms. So these are truly trainings, but we focus more on a digital and an ATAWAD approach, so anytime, anywhere, any device, so you can learn about the twin anytime and anywhere you want. So these production will start to be available in the second semester of 2001, and all the productions will be available in English. So would you be a German, Netherlands speaker, or as myself, a French-speaking guy? You just have to make a little effort and attend it in English, but it's in that sense it is available to everybody. And so, Paul, I give you the floor. Just say to me when you want that I change the slide.
Okay.
For the WP4.
Okay, so go to the next slide then. So I'm Paul Wagner, so I will be coordinating the test cases, and in the overall project, okay, I think there is some timing on the slides that they automatically go forward, so okay, I have to go back.
I don't have this with mine.
Yeah, you have to go back. Yeah,
Sorry,
keep them like that. Otherwise, I can share if you want. Go up.
Yeah.
To the first slide. Okay, leave them like this view. They don't have the problem. So the reason why we have not just creation of courses with available material worldwide in the Interact is because in real life you need to apply it for real in order to know what doesn't work and what it really takes in practice to bring a technology to life. So we have test cases where we want to go to really face reality in different levels, and also to make sure that we focus on what's really a digital twin. Because as Klaas already said, there are lots of bandits on the horizon who like to capitalize on a hype by just taking the label and keep doing what they have been doing so far. Next slide, please. So we, yeah, you don't see the full slide. If you zoom back in, Francois, everybody can see the full slide. You're zoomed in too much. Zoom, yeah, a bit more, a bit more. Yeah, okay. So the first part we have is our short-running test cases in order to have a broad coverage. So what we have is that we invite, and this is say not written fixed in the proposal, but something we take as we get opportunities. And so we get short-running test cases where we start with use cases, like in the started here. What's the purpose? What's the objective? Why would we have a digital twin? And how much investment can we justify to do it? And the next step from the use cases, we go to the domain model. And this is what I've been discussing earlier here in the question and answer session there, is that you use the use cases to know what's relevant, and then you forget the use cases. So it's the relevance and reality which determines what your physical twins will be. And in order to learn early, you select a very limited amount of parts in your application domain, and you start modeling them, and you start modeling them simple, and you expand as you go. You don't hesitate, you don't postpone by being afraid that what you're doing is wrong, because you learn early. You might discover that your first efforts need to be thrown away and that you have to restart, but because you limit your effort, that's not a problem. So you grow into that, and you really forget about what the use cases are. You only remember what's relevant in the domain. That's the for the short-running test cases where we go interactively with the partners who are interested, is that it's not high commitment to get involved with us, in the sense that I expect a lot of those cases to go to the first two steps. You have some use cases, you go to the domain model, and then you learn that it's too early or too marginal for you, and there it stops. But in the meantime, you know what digital twins can mean for your organization, and you know when to start looking into them again, or you're better able to talk to other parties about digital twins. For others, it might be very relevant, but not the best time to start doing it, because say 9 months later you're going to start a project where it fits perfectly, so then you postpone. And in some cases you will discover it's an opportunity you don't want to miss, and then we intensify. Next slide, please. A much more limited number of test cases will be executing during the entire project, and this is where we're going to really test out what it takes. Most of them will be Industry 4.0 test cases. I will be doing one which is digital twins in everyday activities in the social sector, just to learn how you can deploy digital twins when there is no big economic leverage to recover your investments, but where the scope of deploying them in the end can be really viral and very big. We are looking at what I call the mama papa taxi problem at a house where children whose parents cannot take care of them are, say, taken care of. And it's about the volunteers who need to coordinate their activities with the organization to organize everything. That's a high aiming target, but even if we achieve our goals very partially, I mean, the problem I have there, if I go to workers in a factory, I get a much easier problem to which I can apply the same results. Next slide, please. So the way the work package on test cases work is to be agile and responsive. So our outcome depends on the interaction with the test case providers. We want to have a larger number of short test cases, so we get a feeling of what's there in the environment, in the economy. A smaller number of short test cases which go beyond the initial get to know, And then a small number of what I call reconnaissance in force. These are the long-running test cases so that we can learn what it really involves and feed this into the courses of work package 2 and 3. Next slide. So I'll be in charge of this work package. So talk to you, Flanders Make or whatever with your twinning organization, and also contact me in order to get involved and see how the Interact can be relevant for your organization.